In the wild world of AI, there's a story playing out right now that is a classic David versus Goliath tale. It's a story that flips one of the biggest ideas in the entire field on its head and asks a really simple question that has a totally shocking answer.
For years now, the race in artificial intelligence has really been about one thing: size. The whole assumption has been bigger is better, period. But is that really the whole story? Today, we're going to dig into some amazing research that challenges that very idea.
All right, so first things first, let's set the stage. The current world of AI is pretty much dominated by one single powerful belief.
Yeah, the thinking has been pretty straightforward. If you want a smarter, more capable AI, you've got to make it bigger. That means you feed it way more data, throw more computing power at it, and, this is the big one, you add more parameters. Now you can think of parameters as all the little knobs and dials inside an AI's brain. The more knobs it has, the more complicated the stuff it can learn.
And listen, when we say bigger, we mean absolutely enormous. Just look at this number, 671 billion. That's the number of parameters for a major large language model, an LLM called Deepseek R1. It is a true giant built completely on that bigger is better philosophy.
But this is where our story takes a really interesting turn. See, just because you're a giant doesn't mean you're invincible. Sometimes, a very specific kind of problem can reveal a pretty surprising weakness.
I mean, these massive models are incredible, right? They can write your emails, summarize long articles, you name it. But what happens when you give them a pure logic challenge? Something like an extremely difficult Sudoku puzzle, where every single move has to be just perfect.
Well, the results are, honestly, shocking. When they tested these huge, sophisticated AI models on a set of super hard Sudoku puzzles, they completely failed. We're talking 0% accuracy. They couldn't solve a single puzzle correctly. So what on earth is going on here?
Well, the answer is in how these large models actually think. They use a process called autoregressive generation. The best way to think about it is like you're writing a story one word at a time. Each new word you write is your best guess based on all the words that came before it. It's a really powerful method, but it has a major weakness.
And here is that critical flaw. For a logic puzzle like Sudoku, if that AI puts one wrong number in one box early on, that one tiny mistake just cascades. It makes the rest of the puzzle totally impossible to solve. And because it's generating its answer in one straight line, the model can't just go back and fix that early mistake. It's locked in on a path to failure. This is where a whole new approach comes into play. If guessing in a straight line isn't working, maybe there's a different way. Maybe AI needs to learn how to think in a loop.
Think about it. What if instead of making one big high-stakes guess from start to finish, an AI could just make a rough draft of the solution? Then it could look at its own work, find the mistakes, and then create a better draft, and then do it again and again, getting closer and closer to the right answer with every single loop.
And this is pretty much exactly what a team of researchers developed. The model takes the puzzle, makes an initial rough guess, then it kind of reflects on that guess to update its own internal reasoning. Using that new line of reasoning, it refines its answer, and it can repeat this whole loop up to 16 times, constantly making its solution better with each pass.
So, with all that said, let's meet the hero of our story, the model that uses this new, loopy way of thinking to do something pretty incredible.
This sets us up for a classic showdown. In one corner, you've got the giants, the large language models, and in the other corner, our challenger, the tiny recursive model, or TRM for short.
Remember this number? This is the scale of our LLM giant, over 670 billion parameters, a true titan.
And this is the size of our challenger. The tiny recursive model has just 7 million parameters. No, that is not a typo. It is less than 1/100th of 1% of the giant size. That's like comparing a skyscraper to a single Lego brick.
So, who wins the Sudoku challenge? This is the moment, right here. While the LLM giant scored a flat 0, the tiny recursive model solved an incredible 87% of the puzzles correctly. A tiny model, just by thinking differently, absolutely demolished the giants on this logic task. It's amazing.
Now, you might be wondering, where did this little genius come from? Well, this breakthrough didn't just appear out of thin air. The TRM is actually a really clever, simplified version of an older, more complicated idea called the hierarchical reasoning model, or HRM.
The real innovation here was all about simplification. See, the older model, HRM, used two separate networks, and was based on these really complex arguments about biology. TRM just streamlined everything. It uses one tiny network, and it focuses on that simple, repeated process of improvement. All that complexity was just stripped away.
So what is the big takeaway from all of this? I mean, how did this tiny model pull off such a stunning victory?
Well, there are a few key secrets to its success. First, simplicity. One network turned out to be way more effective than two. Second, efficiency. Its looping, recursive approach is fantastic for learning from small amounts of data without just memorizing the answers. And maybe the most surprising thing of all, size. The researchers actually found that an even smaller version of the model, one with just 2 layers instead of 4, performed better. In this case, less was literally more. You know, a quote from the research paper itself just sums it up perfectly. They said, "TRM is much simpler than HRM while achieving better generalization." In other words, the model got smarter not by getting bigger, but by getting simpler and more focused.
And that leaves us with a really fascinating question for the future of AI. For years, the only path forward seemed to be scaling up, up, up. But this research points to a powerful alternative. What if the most exciting breakthroughs aren't about building bigger giants, but about designing smarter, more efficient thinkers? What if the future of AI is actually tiny?